To welcome everybody. It's my pleasure to introduce our guest, Antonio Armario from Barcelona, from the Universitat Autónoma de Barcelona. Actually, I can say that we are friends for a long time. We first met on a conference in Slovakia, and since then, I guess it's your second time perhaps, because he was also once in a conference in Debrecen, and I visited twice your laboratory when we did some research together, and we are sharing some common interest on stress research, and then we are discussing a lot in theory what's going on and what would be the future of this stress research. With this in mind, I would like to give the floor to Antonio, please.
Thanks, Dora, for inviting me. The talk will be a conference about some topics I consider very important in the field of stress, but it's not a general view, but only some points we consider which are critical to understand the concept of stress. Yeah. See, one of the first questions about the stress is how to define stress. The definition of Hans Lee was so general that it was difficult to translate this definition into experimental data, and I like very much one definition by Vigas, which is from Slovakia, I think. He said that stress is the state created in the organism when facing situations that represent an actual or potential danger. Actual would mean that you can alter the animal, the homeostasis of the animal, and the animal even can die. Our potential might be that there is something that can increase the probability that you experience some kind of damage. But it's not a real damage. It's only because you expect that in this particular situation you will finish with some danger. And cannot be solved with usual homeostatic mechanism. This is very important. We will see when we speak about systemic stressors. The problem with stress is this: there are changes in so many variables that it's difficult to select which are very important to understand the concept of stress. It's well known that basically when you are in a stressful situation, you activate basically two main systems. One of the systems is the sympathetic nervous system. This means that, I don't know, it works. Sorry, it's here. I cannot point directly. It's very difficult to me to point because the direction is not. Sorry. This is okay. This is the activation of the sympathetic nervous system that activate a lot of different things, but also activate the adrenal medulla to release adrenaline and noradrenaline. The other system is the paraventricular nucleus of the hypothalamus, which release CRF, vasopressin, and other factors which can stimulate the synthesis of ACTH in the anterior pituitary, and the ACTH acts on the adrenal to release corticosterone in rats, cortisol in most mammals and in humans. These are apparently the best study at the most general system of the stress response. In the case, but when you look at the changes in a stressful situation, you can see that we can modify basically all the anterior pituitary hormones. Sometimes in different directions, sometimes increase, sometimes decrease. But the only exception perhaps is the follicular stimulating hormone, which is not very sensitive to stress. But you can change basically all the anterior pituitary hormones. What's important question is, which is the relevance, the physiological relevance of this? Still, we don't know which are the relevance of most of the physiological changes during stress, because we have focused only in a few systems. One particular important aspect of stress is, or stressors are the characteristic of stressors. You can see here examples of physical or systemic stressors, intense exercise, hypoxia, hypovolemia, hypoglycemia, gowns, infection, and so on. This physical stressor means that you can alter homeostasis, and you need to respond to this situation in order to maintain the homeostasis. In the case of psychological or emotional stressors, for instance, the fear to predators, learned fear conditioning, social threats, in this case, you are not receiving a danger to the body, but there is a probability that this happens. So this is an anticipatory response in case you need this kind of response to maintain homeostasis, but it's not because they are directly altering homeostasis. This is important to understand because this is the great difference between emotional and physical stressor. In some cases, the stressor can be a mix of systemic and emotional stressors. This is the case of some laboratory stressor, which is, you can see here, exposure to high-intensity noise, restraint, immobilization, electric shock, forced swim, social defeat, and so on. Sometimes some people say restraint, immobilization are physical stressors. We will demonstrate later which is what I think is the difference between physical and emotional stressor, and you can decide on the basis of this if some cases, for instance, electric shock, which is painful and theoretically is also systemic, which is the main characteristic. You can see on the basis of CFOS expression that we will see later. One of the classical topics about stress research is which is the specificity of the response to different kinds of stressors. Again, if you want to understand the field of stress, it's important to compare physical and emotional stressors. You can see here in a classical paper and data by Pécs and Palkovich, you can see here, for instance, they compare the ACTH, adrenaline, and noradrenaline response to cold, insulin administration, which is cause hypoglycemia, and then is a systemic stressor, hemorrhage, formalin, which is painful, and immobilization. You can see here that when you compare the ACTH and adrenaline response to this stressor, you can see here that there is a relatively good concordance between both, not exactly, but relatively. But if you see here, for instance, the response to hypoglycemia is clearly higher than the response to cold, for instance. In the case of adrenaline and noradrenaline, which theoretically they are released from the adrenal medulla or the sympathetic nervous system, you can see here the dissociation depending on the type of stressor. In the case, for instance, in the case of insulin, there is a much higher release of adrenaline than noradrenaline. This is a rationale for this because the factor which controls the release of glucose into the blood from the liver is basically adrenaline, not noradrenaline. So it has a logical that you can release more adrenaline in this condition. But you can see here that in a lot of cases there is a dissociation between adrenaline and noradrenaline. The main reason of this dissociation is because the adrenaline you can find in plasma is basically from the adrenal medulla. But noradrenaline is both from sympathetic terminals and from the adrenal medulla. So it's not only the activation of the adrenal medulla, it's also from the sympathetic nervous system. But it's clear that when you are using physical stressors, the response to the physiological response is not exactly the same. Sometimes it's qualitatively similar, but not quantitatively similar. In other cases, there are a clear difference. That means that each systemic stressor has some kind of particular signature in comparison with emotional stressor we can see later. You can see here also that in all cases, when you see to the response to immobilization, you can see here with ACTH, with corticosterone, with adrenaline, with noradrenaline, that the response is at the higher level, compared with the response to systemic stressor. That means that immobilization is a very severe stressor, and we have demonstrated it and other people with different approaches. To summarize a little bit about the problem of the specificity of stressors, you can see here my ideas about this is that with systemic stressor, you have a response which is specific for the situation. That means that the response to cold is absolutely, at least in great part, different from the response to, for instance, to hypoglycemia or to hypoxia. However, when the situation is very important and can induce danger in the organism, then you mobilize another response. This is the non-specific response. You sum both. The homeostatic response, which is particular for each stressor, with the non-specific response, which is it will be the classical neuroendocrine response. Which is the problem? The problem is when you are doing this in the laboratory, you are measuring both. So it's difficult sometimes to distinguish between the specific response and the non-specific response. Sorry, it's because it's difficult to control. Apparently this is clear in the systemic stressor. You are mobilizing some specific particular physiological system, and then when the situation is strong, you can mobilize some kind of alarm reaction to zoom to the other response. What's happened with the emotional stressor? This is a big problem because in this case, we are sure, because of the different data, that the non-specific response predominates. But we cannot rule out that there is some specific response to emotional stressor. The problem is this is difficult to demonstrate in the lab, and it's the same question as if we can identify some specific biological response to emotional situation. The problem is that basically is the same. Nobody knows exactly, because at least in my experience, when I read a lot of papers about emotional response and the response to stress, is that you have no possibility to identify each particular type of emotion with the biological marker we can measure in human or in animals. You cannot identify. We have not a particular signature that say you this is happiness, this is sadness, it's impossible to, this is fear, it's impossible to obtain this kind of signature. Perhaps there is some kind of signature, but we don't know exactly, we don't know how to measure or which to measure in this way. So apparently the emotional stressor trigger are basically a non-specific response. Which are the main response? Basically the sympathetic nervous system and the pituitary adrenal axis. When I started studying stress, I was very interested in how to measure intensity. Why? Because we assume that if you are exposing the animal or humans to severe stressor, to more intense stressor, you can use more pathology. So how to measure the intensity is a critical factor. The other question that we will touch a little bit is how to distinguish between different stressor, different emotional stressor, regarding the emotional meaning, predictability, controllability, and so on. We will touch a little bit about the quality, but more about the intensity. The question is, which are the biological markers of stress? When I start working in the field, or a little bit later, we saw some very relevant papers about this, and this is from Nattelson in the States. He used different shock intensities and studied just the peak of the response of adrenaline and noradrenaline. And you can see here clearly that when you look at the peak of the response, it's true that when you increase the intensity of the shocks, you increase the release of noradrenaline. And you can see here that it's the same with with adrenaline, but it's even clearly the increase is higher with adrenaline. But apparently both hormones are very sensitive to the intensity of stressor, as has been demonstrated for other people comparing, for instance, in the case of Kemnatsky, we know very well, they compare different kind of stressor, immobilization and restraint and several ones, and they demonstrate also that the response clearly is sensitive to the intensity of stressors. When we thought about this, we tried to analyze or to understand which are the factors involved in the intensity, and we read this paper from Hennessy and Seymour-Levine, which are classical in the field. They manipulate the condition of the mice in this case. From the situation, the base situation to the 3, they change the condition of the animal in order to become more stressful. But the situation, the last situation contained the other, so you cannot say that they are qualitatively different, so this is the reason for the differential response of corticosterone. I like very much this kind of experiment, and we did a similar experiments in rats. And we were at this time interested in different hormones, not only in ACTH or corticosterone. And we decided to measure basically all the anterior pituitary hormones in the rats. This is the design was very similar to the design by Levine. We increased progressively the intensity of the stressor, each stressor containing the stressor before. And you can see here that there is a very good relationship between the intensity of the stressor and corticosterone, also with prolactin, and we have demonstrated in a lot of different experiments the same pattern. But what's happened when you analyze LH, growth hormone, thyroid stimulating hormone in the same animals? You can see here, with the picture is absolutely different. It's true that all the stressors were modifying the plasma level of these hormones. In the case of LH is increased, in the case of growth hormone is a decrease, in the case of TSH is an increase, but you can see here that there is no relationship at all with the intensity of the stressors. So that means that when you are trying to search for the biology of stressor, if you are interested in the intensity, you have to select very well which variable are you measuring, because otherwise you don't know exactly which is the intensity of the stressor you are using. This is important. In fact, after reading a lot of different papers in the literature, everything about this in humans and in animals, basically only catecholamines, ACTH, corticosterone, depending on the condition, prolactin are sensitive to the intensity of stressor. I don't know any other parameters in the literature of stress that can in some way say you which is the intensity of the stressor you are using. Which is the problem with corticosterone glucocorticoids? The problem is that when the ACTH is increasing the level of ACTH, the adrenal saturate. This is the example, this is in dogs, a classical experiment with dogs. In this case, they administer a different dose of ACTH, and you can see here in the peak of the response, you can see here that after some levels of ACTH, the corticosteroid response is maintaining. This is because the adrenal saturate. It's impossible to secrete more corticosterone. If you follow not the peak, but the area under the curve for a time after they reach the basal levels, you can see here that there is a very good correlation between ACTH and corticosterone. Which is the problem? The problem is that most of the people working in the field of the stress only measure corticosterone and only measure in one particular point. So you cannot deduce on the basis of this data which is the intensity of the stressors. The other question is that not always, not because of the saturation, but for other reasons, not always corticosterone reflect ACTH or vice versa. This is the case, for instance, when you expose the animals to restraint, in this case, for 1-2 days, in this case, you can see here a huge ACTH response initially, but then the ACTH response decline, and when you have about 6-10 hours maintaining the situation, you can find that the levels are basically as the normal levels. However, if you look at simultaneously what's happened with corticosterone, you can see here that corticosterone response is maintained. It's true that there is a decline, but the corticosterone is maintained at a relatively high level. That means that there is a dissociation between, it's the only way to explain the discrepancy between ACTH and corticosterone. And we know now that this is the consequence of some factors which can act on the adrenal cortex to increase or modify the sensitivity of the adrenal to circulating ACTH. So with the same level of ACTH, you can obtain different levels of glucocorticoids depending on this factor. There are several putative factors which can contribute to this, but the most well characterized is the sympathetic innervation of the adrenal. You can modify the nerve and you can modify the response of the adrenal to certain levels of ACTH. This is very well demonstrated, particularly in big animal, because in rat it's difficult to anatomically focus just in this nerve, but this is clear. Nobody knows exactly which are the factors involved. There are several theories. I think that nobody has studied too much this point, but it's clear that in some cases there is a dissociation between ACTH and corticosterone. If you only analyze cortisol or corticosterone, you don't know. You deduce that all the changes you are finding with cortisol, corticosterone is a reflection of ACTH, but you can see here that this is not the case in some circumstances at least. When you, coming back to the intensity of stressor, this is one of our papers, we compare immobilization with severe Fuchs shock. And you can see here that it's true that the ACTH, corticosterone, glucose response is very similar when you just after the termination of the stress, but you can see here when you follow the response after the stress, you can see here that the recovery is slower, clearly slower with immobilization than with Fuchs shock. That means that even if you are using a very severe stressor like Fuchs shock, immobilization is still stronger. We don't know the particular reason for which the rats are so sensitive to this kind of immobilization, but you can demonstrate in a lot of different experiments. But in addition, we measure food intake, not just in the first day, but in the following days. And you can see here the difference. When you study the changes in food intake with Fuchs shock, you can see here there is a decrease in the next day, but then recover. When you expose the animal to the same time, to the same period of immobilization, you can see here that the decrease is clearly greater the next day, but it took, basically, it takes 1 week to recover the normal food intake. Again, demonstrating two things. One is that we have also the data about prolactin in this case, but I didn't present. But that means that when you classify one stressor on the basis of intensity, when you use one of these markers, particularly ACTH, because it's the marker we have been used always, if you say this stressor is more severe than other, basically all these parameters say the same. That means it's not a particular characteristic of the variable you are measuring. It's something which is clearly different between stressors. Even food intake, which is regulated by a different way than the other hormones. This is a little bit a summary of which is the pattern of changes in some hormone in response to the intensity of stress. So you can see here that ACTH, adrenaline, and prolactin are very similar in the response related to intensity. This is the case of glucose. Glucose is sensitive to a stressor, but only when you are using a stressor of intermediate to severe intensity. Why? Because it's a reflection on adrenaline release. But it's true, it's not the direct measurement of adrenaline, it's a secondary measurement, but it's clear always that glucose can reflect in some way the intensity of stressor. Except see the stressor you are using implies metabolic changes, obviously. If you are exposed, for instance, if you expose the animals for swim, glucose, the release of glucose is lower than you expect on the basis of ACTH, but it's because they need glucose for the exercise they are doing in this situation. So it's a good marker, but okay, you have to consider which is the particular characteristic of the situation. If you look at the corticosterone, it's the opposite. In fact, it's very sensitive when the stressors are of low intensity, but saturate with intermediate level of intensity. That means that you cannot deduce the intensity of the stressor if you are using corticosterone if the stressor is between intermediate and severe sensitivity. One example of the problems when you are relies only in corticosterone is this data. Sorry, well, I advance. I don't know exactly where is the data. I will show you later, so there's no problem. It's the opposite. Okay, I will see you later. When we were doing this kind of experiment in animal, one of the questions is the neuroendocrine response to stress similar in laboratory animals and humans? Obviously, this is an important question when you are trying to relate your research with the human studies. Basically, the qualitative response is very similar. But it's true that the magnitude of the response is clearly lower as compared with rat. For instance, I have read several papers about which is probably the maximum cortisol response to people doing some military, I don't know the name, when they are simulating combat or something like this, and the maximum, typically the cortisol response, the cortisol levels in plasma is about 12, depending on the hour of day, between 10, 12 microgram EDEL, and there is an increase until, for instance, 30 perhaps, not too much. I don't know it because there is a saturation of the adrenaline, because in this case we don't know exactly what's happening in human. But apparently cortisol might be, under some circumstances, sensitive to the intensity of stressor in human, but it's clearly the response is lower than in rats. Then we look, which are the data about the intensity of stressor, not the qualitative response, which is very similar, but how we can measure the intensity of stressor in humans. Surprisingly, I was looking at the data and it was impossible to find a paper dealing exactly with this problem. We did some experiment in collaboration with psychiatrists because I know for a previous paper from these people that when the medical students are doing the exam of psychology, anxiety is lower when they are doing the exam of physiology because they are the physiology is more demanding and they are very anxious when they are doing this. And we read the paper and say, okay, we can collaborate and do this similar experiment but analyzing some hormones. And we did, and you can see here that when we measure anxiety just before the student enter into the exam, you can see here that clearly there was an increase in anxiety with psychology exam, but also with physiology exam, and the response to physiology was greater than the response to psychology. So it was, we expected on the basis of previous data. When we analyze the cortisol response, you can see here that the response was very similar. This is important because we measure cortisol just when the student enter into the exam, not during the exam. So the cortisol response is slow and we cannot measure exactly what is happening with the student. But you can see here prolactin. Prolactin response increased with both exams and were sensitive to the intensity of stressors. So in the case of glucose, even we are measuring glucose, apparently it's very easy, and you can see here that they didn't discriminate, the measure of glucose didn't discriminate, but we can measure the response in humans. That means that basically we have no evidence that the response in humans is qualitatively different than the response in animal in order to measure one particular stressor or the intensity of a stressor. We tried to do another experiment with a third level stressor, but it was difficult to imagine. And I don't know, but at least I don't read any more paper about which are the best marker of intensity of stressor in human. It's clearly surprising to me. I don't know why, because it's a clearly important topic, but apparently nobody is clearly interested in this problem. The other question is not only the intensity. Okay, the intensity is important, but probably the qualitative aspects of stressor are also important. We can identify in some way qualitative aspects. Most of the studies about this topic was done a lot of years ago, and now apparently nobody is clearly interested in this topic. I will put some examples about which is the importance of the qualitative aspect of stressor in this point. One of the most classical model in psychology is the learned helplessness paradigm. This implies that you put three animals. One animal is placed in this box, but they don't receive any shock. In this case, this animal is the master animal, can receive shock in the tail, but they can control when the shock starts. If they move with the head, sorry, it's difficult to. If they move with the head, this wheel a little bit, the shock stops. But this animal is paired with this, but in this case, they cannot control. So they receive exactly the same amount of shock as the master, but they cannot control. When when Steve Meyer did some experiment to measure ACTH and corticosterone in these conditions, you can see here that the ACTH response and the corticosterone response, this is the peak, this is the post-stress period, is basically similar in both conditions. So apparently, at least in rats, the capability to control the situation when you can escape or not from a shock is not altering the biological response, at least the HPA response. What happens when the animal not only can escape but can avoid? Then we did an experiment in adolescent rats. We exposed the animal to hook shot, not to tail shock. In this case, the animal can receive a sound or a light. Then after a period, a shock appears, and the animal can learn to avoid the shock. When the light or the sound appear, the animal can move to the other compartment and the shock doesn't appear. Or they can escape when the shock is present, they can escape to the other situation. But they learn, at the end they learn that they can avoid the shock. In this case, you can see here that when you expose the animal to the first session, there is any difference between ACTH and corticosteroid response between the animal which can control and the animal which cannot control the situation. However, when you repeat the session, it is the session 8, you can see here that all the response has been reduced in all animals, but now the response of the animal which cannot control the situation is higher than the response of the animal that can control. That means that under some circumstances, you can see that some parameters probably are sensitive to this kind of qualitative changes in the stressor. But it's not easy to demonstrate, at least it's difficult, at least in the rats. Another question is, to what extent the response of the SPX is related to other characteristics of the animal. For instance, in this case, we analyze the influence of anxiety-like behavior in the animal. You can define if an animal is more or less anxious on the basis the time they spend in the open arm of this apparatus. This apparatus has some closed arms and open arms. Theoretically, the animal which are less anxious explore more time the open arms. We classify the animal on the basis of these characteristics, and then we study which is the response of this animal to a novel environment, in this case a whole boar, like that apparatus. You can see here that the response of the high anxiety, low anxiety animal was exactly the same. With ACTH was the same with prolactin. So apparently, at least the anxiety is not, which is a characteristic of personality also in animals in some way, is not translated to changes in the hormone system or the biological system. That means that biological markers are good. Okay, when you are trying to identify intensity, we have some tools to identify. When you are trying to analyze the qualitative aspect of stressor, it's very difficult to use biological markers to identify these characteristics. At a time, we decided to study what's happening not only at the level of the hormone, but also in the brain, and we start to study the brain processing of stressors. This is a picture also for Pachak and Palkovich, which is to me very important. You cannot pay attention to the different areas. There are a lot of areas, but in this picture you can see cold, hypoglycemia, hemorrhage, pain, the same stressor that they use to analyze adrenaline, noradrenaline, ACTH, and so on, and immobilization. And you can see here is the induction of C4 as a marker of neuronal activation in different brain areas. You can see here that when you compare, for instance, cold, hypoglycemia, hemorrhage, it's true that they activate some particular brain areas. In most of the cases, there is no activation. If you compare the cold with hypoglycemia and hemorrhage, you can see here that the most activated areas in general are different. So there are some specific areas which are activated, and the areas might be different from one stressor to another. When you compare pain, this is the case of pain. Now, if you compare pain with immobilization, if I ask you the overall response of the brain to comparing to pain, cold, immobilization, if you ask you how you will classify pain, as emotional or a physical stressor, you have to decide between both. Which is your decision when you look at this picture? Is more an emotional or is more physical? Only you compare the picture. You compare immobilization and pain. It's clearly the main component of pain, or in the case of Fuchs shock, the main component is emotional, because the picture is very clear. It's not a physical stressor. That doesn't mean that there is not a contribution of physical aspect, but the main picture is emotional. So in the discussion in the literature about sound stressor, physical or emotional, I have a clear idea about this. For swim, noise, Fuchs shock, or are mainly emotional stressors, because the pattern of the response of the brain is very similar to typical emotional stressors. When you try to identify which are the areas involved in the regulation of the HP axis, for instance, is an example, the HP axis, in response to different stressors, I summarize this in this picture because it's difficult, there are a lot of different stressors, but you can see here that when you are exposing the animal to physical stressors, the signals eventually arrive to the brain stem, particularly the nucleus of the tractus solitarius and some related areas, and then you activate these areas, and these areas directly send inputs to the paraventricular nucleus of the hypothalamus. If you are using some other kind of systemic stressor, you can activate some circumventricular areas, and these areas project directly to the paraventricular nucleus. So it's clear that you can activate very quickly and very directly the PBN with systemic stressors. Even you can activate the system peripherally through the nerve vagus. The vagus nerve. You can activate, there is, for instance, in the case of cytokines, some of the cytokines have been demonstrated that there is receptor in some cells of the vagus, and the binding of the receptor activate the system, and then you can induce a reflex that activate the HP axis, acting peripherally, not directly within the brain. So this is the picture with physical stressor. The problem with the emotional stressor is that you activate basically, as we saw before, a lot of different brain areas. This is only a picture of one of our data with immobilization. This means, as compared with the basal condition, this is CFOS in situ hybridization. You can see here that there are a lot of activation in different brain areas, as we expect. This is the decline when you wait for 1 hour after killing the animal, but it's clear that you are activating a wide range of areas within the brain. In this case, it's very difficult to choose particular areas to be studied because there is a general activation of the system. But in any case, we know that the emotional areas of the brain, the prefrontal cortex, amygdala, lateral septum, these areas has no direct connection with the PBN. So when you are experiencing emotional stress, you activate a wide range of telencephalic areas. These areas has to connect with other areas to activate the PBN. this is a polysynaptic way which is very complex to understand, but it's clear that most of these areas can project to hypothalamic nucleus, which in turn project to the PBN, but it's always polysynaptic. One of the most important areas in this regard is the bent nucleus of the stria terminal, which is here. Because the bent nucleus is close related to the amygdala, is a telencephalic area, but is the only telencephalic area which directly projects to the PBN. So there are a lot of studies trying to identify whether some of the higher level emotional areas activate the SP axis, acting previously on the nucleus of the stria, on the bent nucleus of the stria terminal, and then the nucleus project to the PBN. But it is clear that the picture is very complex, and it's very difficult to choose one area to study. In fact, when you look at all the studies about the lesions in different brain areas and the activation of the SP axis, it's almost impossible to eliminate the response. In some cases you reduce the response, in some cases you increase a little bit, but always the response is basically maintained. It's difficult to explain because in our classical view, if you lesion some area that project to this to the PBN, you can eliminate the response, but it's not true. I think nobody knows exactly what is happening, but probably it's because there are multiple pathways to activate the SP axis. So you need to touch not one, but several pathways to, there is some redundancy in the system that allow us, that it's impossible to eliminate completely the response. Probably this means that the activation of the SP axis is very important for the stress response, because if you cannot eliminate even with lesion in particular brain regions. To give you an example of an important question regarding physical, again, and emotional stressor, this is a study, very interesting study, because they compare hemorrhage, interleukin-1 beta, noise, restraint, swim. They compare the activation in the PBN and then the CFOS expression in two particular areas of the amygdala, the central amygdala and the medial amygdala. In the classical view of the central amygdala is like the mediator of basically all response to emotion and to stressor. But you can see here that this is not the case when you analyze CFOS in response to stress. You can see here how the response of the central amygdala was greater when you use physical stressors as compared with the emotional stressors. Even if the intensity in some cases is clearly different in some cases. This is the case of the central amygdala, but you can see here the case of the medial amygdala. In the medial amygdala, the response is basically to emotional stressors, not to physical stressors. That means that probably the areas involved in both aspects are clearly different. But if you look at the classical books about the control of the stress response and emotional response, the central amygdala is the most important nucleus. The medial amygdala, basically nobody mentioned the medial amygdala, but in the case of the stress and the emotional stressor, probably they play a critical role, at least in the regulation of the SP axis. Because we were clearly interested in intensity, again, when we start doing CFOS experiment, we know that in some areas, apparently, the response of CFOS was very similar independently of the intensity of the stressors. So we decided to do some experiments to compare stressor, and you can see here how this is the response to the ICT response to open field, to cut odor, and to immobilization. You can see here a huge difference between the stressor. Immobilization the response is much greater than others. You can see here the C4 expression in the PBN. Basically, there is a very good parallelism between ACTF response and C4 response in the paraventricular nucleus. If you look at the response in the lateral septum, the ventral part, which we know is very sensitive to stress, you can see here also that this area can discriminate well between the different intensity of the stressor. But you can look to the other areas in this case. This is the cingulate cortex. It's complicated. This is the hippocampus, the dental gyrus. This is the CA1 region of the hippocampus. You can see here, surprisingly, that the intensity of the stressor is just in the opposite of the C4 expression. This has been replicated in part by other groups in the States. That means that when you analyze all the brain, a lot of brain areas, we have done this in several experiments, only a few areas within the brain are sensitive to the intensity of the stressor. These areas are basically the PBN, the lateral septum, the medial amygdala, perhaps in some cases the locus ceruleus, one particular brain stem area. But in most of the cases, the response of C4 is absolutely independent of the intensity. But in the case of the hippocampus, and in some cases in the prefrontal cortex, is the opposite. It's a lower response when the stressor is of high intensity. I don't know, later we can discuss, if you are interested, about this point, which is the meaning of this pattern. But this clearly demonstrates the same as we demonstrate with hormone, is that only in some particular cases you can identify the intensity, but in most of the areas you don't know exactly when you are measuring. If you are not comparing a stressor, you don't know exactly which is the meaning of this activation. This is the case. We ask, is because C4 is not sensitive, or is because the areas are not sensitive? And then we decided to analyze another parameter of neuronal activation, which is the phosphorylation on histone H3. We found exactly the same pattern with C4. Sometimes there is a little difference between both, but basically the message was the same. Is in some areas there is a positive relationship with intensity, in a few. In some cases, in most cases there is no relationship, and in some cases there is an inverse relationship. This is the main conclusion. I think we can discuss a little bit more about this if you want. One other topic we have been studying is the chronic stress. Because chronic stress apparently is very important in order to explain the pathology associated to stress. It's true that in the last decades, a great attention has been paid to single stress exposure because of the PTSD, post-traumatic stress model, but in general, the interest, at least for decades, was about chronic stress. In this case, we also started studying chronic stress. It's only a summary of some of our results, but when you are studying chronic stress, there are different models. I think that it's important to choose the model in function of the interest you have in some particular aspects. The typical models are the chronic intermittent and repeat stress, chronic intermittent variable stress because you change the type of stressor, or chronic continuous stress that in the case of laboratory is very difficult to mimic. Perhaps some kind of social stress model when the animals are living together is a model of continuous chronic stress. But depending on the interest you have, you can focus in one of them. In the case of the chronic unpredictable stress, here This is probably the most widely used animal model to induce depression-like behavior in the animal, because apparently you simulate what's happening with human, that you are changing the time of the stress, the type of stress continuously, so you introduce a great variability in the system. But if you are interested in other aspects of stress, you can use, for instance, repeat exposure exactly to the same stressor every day. When you try to identify which is the consequence of this kind of stressor on the organism, it's important, again, to distinguish between stressors of different intensity. And this is only a summary of the changes we expect. For instance, when you expose the animal to low-intensity stressors, is the case, for instance, of noise exposure we used a lot in the past. If you analyze body weight, food intake, adrenal weight, thymus weight, reproduction, the immune system, apparently nothing happens with this kind of stressor. That means that if the stressor is not very severe, it's very likely that you cannot find any important changes in the organism. If you are using intermediate intensity stressor, in this case you start finding some changes in some physiological aspects, for instance, body weight, perhaps reproduction, adrenal weight, but there are no clear changes in this regard. Only when you use high-intensity stressor, you can find the classical picture that the textbook describes when you are exposed to stress. But this only when you are using severe stressors, not with a typical laboratory stressor. In this case, obviously, you decrease body weight, decrease food intake, increase in the adrenal weight, a decrease in the thymus weight, and you can affect reproduction and the immune system. But this is important because not always that you are doing chronic stress, you can find a lot of changes. Only if you are interested in some aspects of stress which are not to induce pathology, you can use low or intermediate intensity stressor. If you are particularly interested in induce some kind of pathology in this case, it's important to know that you have to use high severe stressors. As an example of how you can misinterpret the results, when you are, in this case, when you are using chronic stress, is some of our data. Here we expose the animal to repeat immobilization for, I don't remember exactly, but about 2 weeks, something like this. And then we expose the animal the last day to, again, to immobilization. And we measure ACTH and corticosterone. You can see here that when you analyze ACTH, when the animal was chronically exposed to the same stressor, there was a huge reduction of the response. It still maintained a great response, but the reduction was very clear. But what's happened when you measure corticosterone? If you measure corticosterone, you can see here that the response is higher than in stress-naive animals. That happened in some experiments in the literature, and the people interpret this in the way that when you are exposing the animal to severe stressors, you can induce sensitization of the HP axis as consequence of the severity. But here it's clear that the animal adapted to chronic stress. If you look at the CTH, which is the best reflection of what is happening in the brain, but if you only analyze corticosterone, you misinterpret the results. This was basically repeated in another experiment years later. Here we measure ACTH, corticosterone, just after the stressor, and we follow the response in the post-stress period. We analyze the response and we calculate the area under the curve of all the response. You can see here that after few experience with the immobilization, there is a huge decrease in the ACTH response, and basically the reduction is maintained. There is not a progression in the decrease. But if you analyze corticosterone, at the same time is below. I cannot control this, it's very difficult. Here, you can see here that the peak of the response is higher when the animal has experienced previous stress. It's like in the previous experiment. However, when you follow the post-stress recovery, you can see here that there is a faster recovery of the post-stress response when the animal have experience with the stressor. So you don't know just in the peak of the response, but you note in the recovery period that the animal has previous experience with the stressor. If you analyze the area under the curve, it's clear here that basically this is the significance. You can see a decrease, but the further decrease is very low. Basically, there is no further decrease. In the case of corticosteroids, it's a little bit more, but basically, the most important reduction was in the few days, after the few days of stress. Because we were interested in which are the factors regulating the reduction of the response to chronic stress, everybody assumed that the adaptation of the HP axis, the response of ACTH, corticosterone, follows the rules of habituation. The rules of habituation means that basically the decrease is positively related to the number of exposure and the length of daily exposure, but negatively related to the interval between exposure and the intensity of the stimulus. Then we hope some data that don't fit with this idea, because when we expose the animal to immobilization and then again to only after one immobilization, again to another immobilization, even weeks later, there is a reduction of the response. Sometimes not in the peak, but in the recovery, always. We have repeated the experiment, I don't know how many times, that is always the same pattern. So we were not in accordance with the idea that it was an habituation phenomenon. And then we do a lot of systematic experiment with different stressors, with different conditions, to demonstrate that the adaptation of the HP axis to repeat stress doesn't follow the rules of adaptation. This is a summary of the picture. You can see here that in the case of habituation, the intensity reduced habituation. We demonstrate that with intensity there is more adaptation when you calculate the difference between the first and the second exposure. With daily exposure, is both predict that there is a increase in adaptation. With the number of exposure also, although the contribution of the number of exposure to adaptation is not spectacular, but it's true. But always with the interval between exposure, again, the habituation predicts that there is a reduction of adaptation, and we find an increase. So it's clear that the reduction of the response of the HP axis to repeat stress doesn't follow the rules of adaptation. The rules of habituation. We don't know exactly which is the phenomenon involving, because it's difficult to study, because we don't know which area manipulate, which factor manipulate, but it's clear that there is not, it's a different phenomenon from habituation. We don't know exactly which are the differences, which are the areas involved. Another topic is if we can find a biological marker of acute stress, some biological marker, which is the case of chronic stress. In the case of chronic stress, basically, I think we have not biological markers, real biological markers. But when some people start measuring cortisol in the hair, and they say that could be a reflection of all the release of glucocorticoids for a period of time, we decided to do the same experiment in rats in order to demonstrate whether or not glucocorticoids is a good marker. And then we did several experiments. This is a summary of some of them. We exposed the animal to chronic unpredictable stress. We exposed the animal to chronic immobilization, both severe. And you can see here how the increase in hair corticosterone is clear with the two stressors. We manipulate different systems, and the conclusion is that hair corticosterone clearly reflects what is happening in the animals. But we also ask about the possibility that the system saturate. Then we use a preparation of ACTH, which is very well known in humans, because there is some pathology that need this kind of preparation. In this preparation, there is a slow release of ACTH over the day, so you can find a huge increase in corticosterone for 24 hours. We did this with two different doses of this preparation, and we measure hair corticosterone in this case. You can see here that there is an increase, dose-dependent increase, but you can see here the level where, in this case, about 300 from 10, 20, that means that it's basically impossible that the system saturate. So they can reflect the increase in corticosterone, and also it's impossible, so you can use any kind of stressor in the nature that you will not saturate the system, so it's a good marker. You can see here that the increase after stress is double, is from 10 to 20, and here is from 10 to 300. So it's clear that the hair corticosterone can reflect the chronic release of corticosterone. So if you measure cortisol in humans, probably it's true that they can reflect a period of chronic stress. In fact, when I only present one data in humans, this is a study I like very much, because he compared hair cortisol in humans in German people. This is the people living always in German. This is the immigrant who has adapted very well to Germany, and this is the people who are asking for asylum, seeker asylum. You can see here that there is a huge increase in cortisol levels in hair in this kind of people. So apparently, also in humans, hair cortisol can reflect the amount of cortisol release over a period of time. The problem is, if the intensity of the chronic stress is enough to show a clear increase in cortisol level. It's the same in rats. If I didn't experiment, but probably if I use chronic noise stress and we measure hair corticosterone in the rat, there will not be too much increase. Because the intensity of stressor is clearly important in order to demonstrate that. But it's true that probably it's a very good tool to study which has been the release of cortisol for a period of time, typically in humans, depending on the amount of the size of the hair you use. You can measure the last month, the last 2 months, the last 3 months. Basically, this is the typical study. But it's a retrospective of the cortisol release. So now this measure is extensively used in any human study. So it's an important tool. If we try to look at other systems in order to know whether other systems are responsive to chronic stress, or you can identify some markers, I think that there is not clear marker of stressor intensity when you try to analyze metabolic parameters, cytokines, or everything. There is not any demonstration that there is a proportion between the intensity of a stressor and the measurement of these factors in plasma, for instance, in plasma. One of the most studied system today is the immune system. Some people are measuring cytokines in plasma. When you analyze the result, apparently there is no clear relationship. You can find some changes in cytokines after chronic stress, but it's not clear that there is a reflection of the intensity of stressors. When you try to see what's happening in the organism when you are exposed to chronic stress, it's important to consider not only to measure plasma or saliva, hair, cortisol, something like this, but also to go beyond this simple measurement. One of the experiments, the studies I like very much is this from Miller in the States. They use the caregivers because they are very stressed, chronically stressed, and they studied perceived stress in this population, and they showed there is a clear increase. They analyzed the cortisol levels throughout the 24 hours. You can see here that there is, in some cases, there is an increase in caregivers as compared with control, but it's not a clear increase after chronic stress. But however, when they analyze the glucocorticoid receptor at the nuclear factor kappa beta in the circulating lymphocytes, you can see here that there is a decrease in the glucocorticoid receptors, and there is an increase in this factor which controls the immune system. That means that you need to analyze not only circulating levels of cortisol or something like that, but you need to analyze what is happening in the tissues which are responsive to this kind of situation, because in this case, even if you have normal or even greater cortisol levels, the number of receptors is decreased, so you cannot restrain the immune response, and you can find signs of inflammatory increase despite normal or even a little bit increased level of glucose. So in human studies, I know because I am collaborating with people in human, is not the same as animal, but I think we can go beyond the classical level and to analyze a little bit more what is happening, and we have the possibility to do this because we need a more complete picture about what's happening with chronic stress in humans. Okay, to summarize some of our interests, I think that in the field of stress has been extensively studied from different points of view, but I think that we need more information about conceptual aspects of stress, because I like very much, at least to me, is important. Which are these aspects we need more information, more studies, is most of the aspects related to the concept of stress, the contribution of qualitative aspect of stress to the biological response, how the brain processes stressor, which is the role of some particular areas in stress processing, not only in the response of the HP axis, but in other responses. If we can find appropriate biological markers of acute and chronic stress, still at least in chronic stress, we are not sure about this. And also, which are the real implications of chronic stress in physiopathology and psychopathology and psychiatry, because sometimes when you speak with other people about stress is bad, is a problem, but I am not sure about this, because probably if you are exposed to, not to severe stress, or obviously, but you are exposed to normal stress in life, I think it's not necessarily it has negative consequence of the organism. So we have to distinguish which kind of stressor, which characteristic, in order to be sure that you can induce pathology. So we need more information about these consequences. And this is some of the people who has contributed to my research over the year. This is a more recent picture. Obviously, most of the people are not in the lab, and thanks for all. So if you have some question, I can ask.
Thank you very much for this very interesting talk, although I spent many years on stress research, but I always pick up some new ideas and questions. And first, I would like to ask the audience when somebody has some question. Because I especially liked, I recognize that many people like the students' study when they compared them after a physiology and then psychology exam. I even picked up some ideas that we can make them make a similar studies, comparing, for example, whether the oral or written tests are more stressful for them. But it reminded me, because at that point your conclusion was that there is no, we don't know what to measure because there is no clear marker. However, at the end of the day, it turned out that perhaps then hair cortisol level might be a good marker. But I was thinking that you did not show, for example, the adrenaline, noradrenaline levels, or is there necessarily a marker in the blood which reflects the intensity?
In the case of acute stress, I am very confident that adrenaline is very good, and noradrenaline probably also. In the case of chronic stress, no, because the problem is when you are thinking about chronic stress, you think about chronic stress induce an impact, but this impact basically is in the basal level of the system. And in this case, it's not easy to find an increase it probably on the basis of animal studies, when you are exposing the animal to chronic stress, there is an increase in the activity of the tyrosine hydroxylase, the enzyme which control the synthesis of catecholamines. Also in the brain, in some areas of the brain, there is a clear increase. If you stop chronic stress, then the animal recover. And this is, I think, is very similar with the SP axis also. So it's very difficult to find increases in the basal levels, even if you are chronically stressed, unless you can analyze what's happening in the adrenal or what's happening in the brain, but it's not the case in humans. So in humans, in the case of chronic stress, is a problem because we cannot, the possibility to objectively measure what's happening with human, if some people say, I am very stressed or not, it's very difficult to know. Even it's interesting because at least with acute stress, when you, in animals, but also in humans, when you ask people how stressed are you on the basis of some pictures on, in general, there is no correlation between the cortisol response or the HPX response and the subjective response of the subjects. So there is clearly a dissociation between both. So in this case, what is important? The opinion, the subjective opinion, or is important the biological response? We don't know exactly because it's difficult to do studies in the regard. So we have not any tool that to study chronic stress to demonstrate if you have more or less stress in chronic situations.
So then what do you think about the saliva amylase, for example? Because some people said that it reflects the sympathetic
it's the same
activity.
It can reflect the sympathetic system. In fact, we, in collaborating with my wife, with Rosé, we have done this. It can reflect the sympathetic activity, but it's not clear that it can in some way measure something after chronic stress. Acute stress is clear that there is an increase. Even I don't know, because we have not done the experiment, that I don't know if there is any experiment to demonstrate that alpha amylase in saliva is related to the intensity of stressor. Because this is to me, it's difficult to understand that nobody has been interested in measuring the sensitivity to acute stress, at least in humans. I have tried to do this kind of experiment, talking with clinicians, or I thought, for instance, in an accident, a car accident, just when you arrive, not the people who have suffered some kind of physical damage, but the other people, I say, we can try to do some kind of experiment in this regard. Say, no, it's so complex to have the permits at this moment. So at the end, nobody wants to know or to participate in this kind of studies. So we don't know exactly which is the response of the humans to traumatic stressor. When you have been exposed to this stressor, we don't know exactly which is the biological response. So I think we can try to do this, but nobody has done. Yeah.
Any further question?
Thank you very much. It was really a fascinating presentation. I do not deal with stress itself. I study temperature regulation, and there is also stress-induced hyperthermia. And actually my question would be that there are some easily measurable physiological parameters like heart rate or blood pressure or temperature, or heart rate variability. Can those be used to quantify the intensity of acute stress?
I didn't present because I have to reduce, but in my review about the biological markers, I analyzed all the literature about this in humans and animals, and there is no evidence that any of these markers mark intensity. Any blood pressure, pupil dilation, heart rate variability, there is no. The problem is that there is no studies directly measuring this, interested in the intensity and comparing. So I have to look all the literature about different tests in humans that describe some changes in some physiological parameters. And the final conclusion is that there is no evidence. In fact, the evidence is in the opposite way, that there are not markers of stressor intensity. But this is only with the data we collect over several years, looking at everything in the literature about this. That's why I am surprised about the lack of interest in this point, because it's critical to think that if you increase more the pressure or heart rate, probably this could have an impact in the future in the organism if you are exposed particularly to chronic stress. But apparently there is not interest in this field. I don't know why, because it's always my question. Why is so the interest is so low? I don't know exactly.
Is there any question?
Thank you very much for the presentation. You mentioned that you can't really do it on humans, especially this one car crash that you're speaking about. So I'm curious to know, what would the next steps be? What's the next thing that you'd be interested in researching now that you found these correlations between ACTH or cortisol? What's the next steps?
I don't. Which is the answer?
Of course. You said it's hard to find humans to participate in your studies, correct? So I'm curious to know, what is the next steps for you? Would you continue with the animal research? Would you try to see what these chronic stressors perhaps do to the rest of the body, or what are you interested in next?
In the stress research, I have done a lot of experiments in animals, but I always read everything in humans because I like to translate the information to humans. That's why I try to do some kind of experiment in humans about this topic. I think we need more information about this, because otherwise, for instance, in the case of the cardiovascular system, which is very important, we need to know this kind of experiment. But it's very difficult to convince people to continue. Now I'm emeritus professor, so I will finish not all, but most of my studies. But I think we need more studies. Obviously, we need more studies in animals to characterize the basis of the neurobiological basis of the stress response and the areas involved. But in humans, we need more studies about this. Not only measure cortisol or saliva cortisol in different conditions. It's to know more about what's happened with stress in human, even which is in human. For instance, controllability, some of these factors, we know that it's easier to discriminate sometimes between the control and not control, because we have a much greater capability to analyze information than animals, so it's expected that you can identify marker of this, but there is no studies about this. Apparently, it was a great interest in some time ago, but not now. I don't know why. But I think we have to recover questions about the conceptual aspect of stress now. But apparently nobody is interested in this. I don't know why. Okay.
No.
I would just like to comment that I was very happy to see that you clearly differentiated between the psychological stress and the physical stress, because my area is pain, and then we collaborate a lot with Dora on stress-induced pain, and also I've started to do some stress-induced pain experiments with some of the colleagues also here. And I'm always criticized that if you restrain the animals in the tube for 2 weeks, the mechanical pain threshold drops by 25%. That's clear. And people say that, okay, but that's physical stress. And I always think that it's psychological stress. And that was...
When you expose the animal to stress, there is a change in pain sensitivity, and it's clear with emotional stressor. But the stressor is mainly emotional. Even if you put the animal into the tube, and because it's the same with immobilization, it's very severe. You put the animal just on the board, but the animal, you release the animal, and the animal behaves normally, so there is no problem. In spite of this, there is a reduction of food intake. There is a lot of changes, but nothing physical, nothing that you can note physically.
But the pain threshold only decreases in the restraint model, not in the variable stress model, not in animals.
But this is chronic.
Yes.
Well, and chronic and acute is different, because we don't know when you expose the animal to chronic stress, obviously you are changing the response. I don't know exactly in which direction, but you are changing the response. I don't know, because I don't remember the data, if when you expose the animal repeated to the same stressor, there is a decrease, there is a change in the pain sensitivity. There is a reduction. You can find a reduction, but I don't know if then recover or not, because I don't remember this kind of study.
For 4 weeks, it doesn't recover.
It's the same. Basically, it's the same. No?
It develops after 2 weeks, and it's maintained for 2
Yeah.
weeks. We didn't go further, but we wanted to see something similar to like fibromyalgia, which is
Yeah,
a
yeah.
psychosocial distress. There is no fibromyalgia model in animals, but this kind of
Yeah,
mechanism
yeah.
is a bit related.
But chronic and acute is different, because that is important to distinguish, because you have not expect the same result with chronic and acute stressor. Yeah. Okay.
No more questions, then thank you once again.
Then thank you for your talk, and thank you for participating in the project. And on behalf of the Hungarian Academy of National Scientist Education, I would like to hand you the certificate for your achievement and for your help. And we look forward to your further contribution and helping our students further on in their research. Thank you very much. And also this little present is yours.
Thanks.
Thank you for coming.